Hello everybody, this presentation is about measurement of soil thermal conductivity. The content of this presentation, first we are going to explain what thermal conductivity is, then we are going to address the subject of how to measure soil thermal conductivity, and we do that using probes. So there's a second section about thermal needle probes. Traceability to SI units. Then we're going to talk about the systems that Hexaflux offers for soil thermal conductivity measurement, and last but not least, what to expect in soils. So over to the next section.
Okay, so let's start with an explanation of what thermal conductivity is. Simply put, thermal conductivity is a measure of a material's ability to conduct heat. Of course, everyone has a bit of intuition of what that is. So, for example, you'll all know that the insulating material shown here on the top has a very low thermal conductivity, and you'll probably know that a block of metal shown on the bottom has a very high thermal conductivity. And we want to make that intuition into something more quantitative. So thermal conductivity is typically denoted by the Greek letter lambda, although sometimes K or kappa is used, but we'll stick to lambda. The thermal conductivity has SI units of watt per meter Kelvin. Some people actually prefer to think in terms of thermal resistivity. So this is denoted R or rho, and it has SI units of Kelvin meter per watt. But this contains the same information. It is simply the reciprocal value of thermal conductivity. If you know one, you know the other. Okay, so thermal conduction is a heat transfer method that arises from collisions of atoms and molecules on a microscopic scale, and of the movement of electrons through the material. So actually most good electrical conductors are also good thermal conductors. So how does this work on a macroscopic scale? Well, consider this rod, which has a length delta x, and where one side of the rod is kept at a warm temperature T1, and the other side is kept at a lower temperature T2. Then according to Fourier's law, there will be a heat flux from the left to the right through this material, and the proportionality constant between the heat flux and the temperature gradient is what we call the thermal conductivity. So if the thermal conductivity is large, a lot of heat will flow, and if the thermal conductivity is low, then less heat will flow for the same temperatures, of course. Okay, so what are some typical values for thermal conductivity? So I show here a list starting from roughly 0.01 watt per meter Kelvin up to about thousands of watt per meter Kelvin. So typical insulation materials are around 0.03 to 0.05 watt per meter Kelvin. They're really the most insulating materials. Then we have plastics. Plastics are on the order of 0.1 watt per meter Kelvin. Glass is on the order of 1 watt per meter Kelvin. Then we have some alloys like stainless steel, which are already pretty good conductors. They have a thermal conductivity about 13 to 15 watt per meter Kelvin, but they are not as good as aluminum. So aluminum is around 200 watt per meter Kelvin. And then there are some exotic materials like diamond, which have really high thermal conductivities that go up into the thousands of watt per meter Kelvin. But those are really exotic. Yep. Thermal conduction is not the only heat transport mechanism. There are a few other heat transport mechanisms. So for example, material can move or flow, and this can, for example, be forced movement. So you can, for example, pump cooling water around. But it can also be natural convection. So for example, in the pot, if you are boiling water, then the water at the bottom will heat up. It will expand, the density will be lower, and lower materials will flow upwards, whereas colder material on the top will be heavier and will flow downwards. And in that way, heat can be transported through movement. Another thing that can occur is evaporation. So of course, we all know that transpiring is a way to cool. And finally, heat can also be transported by means of thermal radiation. So for example, the molten metal actually glows. So that's radiation in the visible, but also at lower temperatures, materials can exchange heat by thermal radiation. Okay, so now that you have a bit of an idea what thermal conductivity is, let's discuss the thermal needle probes that are used to measure the thermal conductivity. So thermal needle probes, or non-steady state probes, typically contain one or more temperature sensor. At least one is located in the needle. And the needle contains a linear heater that runs along the length of the needle, and it has a known electrical resistance per unit length, so in ohms per meter. And this is used to measure the thermal conductivity. So you insert the needle into the material, and upon switching on the heater, the temperature will start to rise. So as you can see here, plotted the temperature as a function of time. And depending on the thermal conductivity, the temperature will rise either more quickly or more slowly. So basically, the thermal conductivity is determined by measuring the response to heat generated by the probe. And I can make that slightly more precise. So this is basically the same plot, but now I don't have the time axis, but I have an axis, the logarithm of time. And what we need to look at is the slope of the curve. So if you remember this, then you understand about 50% of the principle. So basically, high thermal conductivity means a small slope, and low thermal conductivity means a high slope. Okay. Thermal conductivity is not the only thing that influences the temperature increase. The other thing that influences the temperature increase is the heater power. So obviously, if you heat more, then the temperature will rise more quickly. The heater power that is generated by the probe can be accurately measured using Joule's law. So the idea is that you measure the heater current, the heater resistance is known, and that allows you to calculate the heater power in watts per meter, so per unit length of the probe. Okay, so once you have measured this, you need to analyze the data to determine the thermal conductivity. So here I again have the curve, the temperature, as a function of the logarithm of time. And what you can see is that there are roughly 3 sections in this curve. So there's a first section on the left, which is a transient portion, in which you see effects of the heating of the needle itself. Then there is a linear portion in the middle. So this is known as the quasi-steady state portion, and this is actually the data that is used to determine the thermal conductivity of the material. And then towards the end, you can start to see portions that are dominated by edge or end effects. So basically, you will start to see the finite size of the material and the probe. And this should also be excluded from the analysis. And basically, in the quasi-steady state, the temperature is linear with the logarithm of time. And you can see that the slope depends only on the heater power and the thermal conductivity. So what do? We take this middle portion, we determine the slope, and then using this formula, you can calculate the thermal conductivity. The heater power is measured, so it's known, and the slope you've just determined from the curve. And this gives you the thermal conductivity. That's basically it. Of course, there are some complications. So there are a few things that you need to watch out for. So first of all, it's very important that the temperature is stable before you start a measurement. Because if there is a temperature drift in addition to the temperature change that occurs due to heating, then you can under or overestimate the thermal conductivity, as is illustrated in the graph. So one tip is to record the temperature before you start heating, so that in your analysis you can sort of analyze how stable the temperature was before you started heating. And then in addition, to avoid specimen temperature drift, you typically just need to allow the specimen sufficient time to become stable. And it's also useful to work in a environment where the temperature is stable, for example, a laboratory, but this may not always be possible. Okay, then a second thing to watch out for is mechanical instability. So the probe must be fixed properly, and it shouldn't move during the measurement. So if it does move, then typically you start to see the temperature, these temperature jumps illustrated in the graph. So it can be recognized quite well. Yeah, so advice is to use a lap stand to fix the probe. Okay. Then third thing to think about is thermal contact resistance. So you want the probe to be in good thermal contact with the material that you're trying to measure. So make sure that there is no air gap between the needle and the material. If you need to drill a hole into the specimen to insert the probe, then use some material, that some drilling leftovers that to fill up the hole again. Make sure the diameter is small. In some cases, it can be useful to use thermal grease or thermal paste to improve the thermal contact between needle and the specimen. But do be careful with that. Do not do it with soils, because then you change the composition of the soil, and that affects your thermal conductivity measurement. Okay, so then about the measurement settings. So there are basically only two measurement settings that you have to set as a user, and that is the heater power and the heat time. So regarding the heater power, the larger the thermal conductivity, the smaller the temperature increase. So to get a decent signal, if you have a higher thermal conductivity, you need to apply more heater power. There is a drawback. If you have moist samples, then using too much heater power can cause evaporation, and that creates a bias in the measured thermal conductivity value. So use enough, but not too much. And then regarding the heat time, this basically has to do with the needle size. So the thicker the needle, the longer it takes for the heat to propagate into the material. So thicker needles require longer heater times. Okay, then it's good to think a bit about how deep the heat penetrates into the material. And so to discuss that, I need to introduce another material constant. So this is the thermal diffusivity. It's denoted alpha and has SI units of meter square per second. And actually the thermal diffusivity is related to the thermal conductivity and the volumetric heat capacity in joule per cubic meter per Kelvin of the material. So it's simply the thermal diffusivity is equal to thermal conductivity divided by heat capacity. So the thermal diffusivity describes how quickly the heat propagates through the material. So the penetration depth is given by the square root of the thermal diffusivity times the time that the heat has been propagating. So you can basically see this as the propagation of an isotherm through the material. So at some point it will be here, and then at some later point it will be there. And I've given here the thermal diffusivity for some typical materials. So for plastics, it's about 0.08 millimeters square per second. For quartz, it's roughly 1.2 millimeters square per second. And you can see that if thermal diffusivity is higher, it propagates faster through the material. So after 180 seconds in quartz, it will be about 30 millimeters radius into the material. Of course, once this heat wave sort of reaches the end of your material, then your measurement will be affected by whatever is around that material. So you should consider your specimen diameter. So from this, I would say it should be at least 60 millimeters, preferably a bit more, maybe 100 millimeters. Okay, so here's a short summary of the tips and tricks. So make sure that there's good contact between the soil and the probe. Avoid thermal contact resistance. Make sure that the probe is thermally and mechanically stable before you start the measurement. Heat enough, but not too much. Make sure that you have a good signal, but if you heat too much, you get evaporation. Yeah, make sure that the material around the probe is sufficient. And it's always useful to analyze your data visually on a computer after the measurement. Most measurement devices will calculate an initial preliminary result for the thermal conductivity, but it's always good to look at your data and see if something went wrong. Okay, so then let's talk about the traceability of the measurement to SI units. Remember, this is the measurement equation, and so basically to make sure that the thermal conductivity that we measured, the quantity on the left of this equation, is traceable to SI units, we need to make sure that all the units of quantities on the right are traceable to SI units. So let's start with the heater resistance. Let's see if this works. Yes. Okay, so the heater resistance per unit length is determined during production. It can be found on the probe itself, so it's engraved on the probe, and it can also be found on the calibration certificate. And this is literally determined using a calibrated ruler and a calibrated multimeter. So basically this is traceable to the units of meter and the units of ohm. The next quantity we need to look at is the temperature. So the temperature is measured using a thermocouple that meets a certain standard, and the standard fixes the relation between the temperature and the voltage. Of course, now I shift the problem from measuring the temperature to measuring the voltage. So we need to worry now about this voltage. And there's a few other quantities, namely the heater current, I, and time t. And basically all three quantities depend on the readout equipment. So basically what we need to do is we need to make sure that we use a calibrated amp meter to measure the heater current. We need to make sure that we have a calibrated thermocouple readout device to measure the temperature. And actually time turns out to be a little bit special. So it does not need to be traceable to SI units. And then you wonder, okay, why? This is actually because of the way that time enters this measurement equation. So it only enters the measurement function as a difference of the logarithm in time. And the result is that the units cancel out. So time does not have to be traceable to SI units. That does not mean that there are no requirements for your clock. So your clock frequency must be stable. And of course, the 0 point in time needs to coincide with the heater switching on. So this needs to be correct. But basically, if you have this, then the thermal conductivity is traceable to SI units. Now you can also do a calibration against a reference material. So then you measure the thermal conductivity sort of relative to that reference material. This requires that you have a material with a known thermal conductivity. Some common materials are PMMA, glycerol, or agar gel. So HuxFlux offers these CRC calibration reference cylinders. So they basically contain a block of PMMA. There's a hole drilled in there such that you can insert the needle. And there's some glycerol in there to make sure that there's good thermal contact between the calibration reference material and the needle. So this PMMA is produced in a way such that it's isotropic, so that's important. And HuxFlux has 3 different hole diameters available for needles of different sizes. So how do we do it then? You insert the needle in your calibration reference material. You measure the thermal conductivity. Then you compare it to the known thermal conductivity of your reference material. So basically you determine a calibration factor. And if you see that this, so ideally this should be 1, but if you see that it deviates too much, then you can adjust, and typically we do that by adjusting the heater resistance. Now this works as long as you use the same readout equipment. If you change readout equipment, then you should redo the calibration. And the reason is that this calibration, although you adjust the heater resistance, this is actually calibration of the entire measurement system, so probe and readout equipment. So it's not per se set that it is the heater resistance that needed adjustment. Okay, so then there are some other useful tools, namely the guiding tubes. Sometimes it's difficult to insert a needle into a very hard or semi-hard material. It may bend or break. So these guiding tubes can be used either to push them into a semi-hard material, or you can cast them into cement. And basically the needle can be inserted into the guiding tube. And that effectively creates a thicker needle. So remember, thicker needle meant slightly longer measurement time. But it has no influence on the calibration. It might be wise to put a drop of glycerol into the guiding tube such that there's good contact between the probe and the guiding tube. And again, there's 3 different sizes of these to accommodate needles of different sizes. Okay, then I give the floor to Kees.
So at HuxFlux we sell systems for measurement of soil thermal conductivity. So let's talk about those. In soils there are 2 major applications where you apply soil thermal conductivity measurements. First of all, for high voltage power cables. Those cables are buried underground, and the general idea is that they have to be kept cool. If they get over 80 degrees C, they start to degrade, so you always want them to remain below that, and for that, at a certain current, the better the soil conducts, the better the heat generated by the current is fed away. So the purpose there is to measure the properties of the soil and to calculate the cooling. Another application is in oil pipelines. Oil is a viscous fluid. It has to be pumped. It's usually heated to attain a lower viscosity, and for that oil pipelines are typically insulated. So there the soil contributes to the insulation of the oil pipeline if they're buried underground or on the sea floor, and actually in that application is beneficial if the soil does not conduct so very well, because that contributes to better insulation. The general idea in high voltage power cables is that in some cases you can save money. Copper costs money, and if you can generate more heat, you can reduce the copper diameter. In oil pipelines, the same thing applies. If the soil insulates, you don't have to apply additional insulation material. So it's all about costs. The first system that we sell at Huxley Flux is our FTN01 system, field thermal needle. It consists of a 1.5 meter rod plus a needle at the end. And here you see a picture of the system in use. It also contains a handheld readout and control unit. So an operator drills a hole to the approximate burial depth of the electrical power cable, and typically that's 1.5 meters below the soil. Then you push the lance, as we call it, in that hole, and the last bit you push the needle in the undisturbed soil. Then you wait a bit until you reach thermal equilibrium, and then you start the measurement. A typical measurement duration is about 5 minutes for this needle type. Of course, depending on the situation, you first have to wait until there's stability. That might take longer than the actual measurement. This FTN system is used on site, so field use, at a depth of 1.5 meters, and it's designed for robustness. The needle diameter is about 6 millimeters, so that can withstand a lot of force and rough handling. So what you will buy as a user is the whole system, including the lance, a needle, a spare needle, the readout unit, a container for glycerol fluid. You have to purchase the glycerol locally and you put it in the container so that you have a local calibration. Then chargers and adapters to charge the battery, which is inside this readout unit. This system can also be complemented with the same readout unit. You can also buy a laboratory version that's called the MTN, and this has a smaller needle, and if you want to perform measurements on a laboratory sample, then you can insert that needle connected to the readout unit that you're also using for the FTN system, and you have the possibility to analyze smaller samples. This diameter of the needle is about 3 millimeters, so it's slightly more vulnerable. We also have other systems, TP-Sys. They have very thin needles, about 1 millimeter, 1.6 millimeters. Also the needle length is smaller. order of magnitude of 60 millimeters length is needed here as a minimum of insertion. The previous MTN needle was 100. The FTN was 170 millimeters. This system is really for two uses: scientific, the measurement accuracy is higher, and some samples are also really small. For example, sediment samples or sediment cores from offshore applications. So there you buy a system with a box, and the box is basically part of the system connected to your PC. So you get your sample, needle, the box, which we call measurement and control unit. You have to connect that to power, so there's no batteries on board, and you connected it to your PC or laptop to operate the whole system. So TPSys is the system name, lab use, high accuracy, and a special application for sediment specimens. So last subject, what can we expect in soils? So you perform a measurement, and the question is, okay, what kind of results can realistically be expected, or how to approach the whole measurement. So one thing to keep in mind, in the high voltage power cables, a perfectly dry soil is considered as the worst case situation. So in order to assess the situation for high voltage power cables, what people typically do is first they start analyzing their soil type. So they classify it. And some parties have the possibility to do a particle size distribution measurement. That is also very useful. If you do a thermal conductivity measurement, this dry condition is most relevant because it represents the worst case situation. So you might see some laboratories drying out the sample to determine that condition. Also of interest may be the saturated condition. For example, in oil pipelines. Also useful to keep a record of the dry density of the soil, or the density at which you perform the measurement. And of course, dry density and saturated density are valuable pieces of information. So this is typically possible in conditions in the laboratory. What you should also realize is that if you perform a measurement in the field, in many ways that's a dangerous measurement, because you have no control over the moisture in the soil. And we get back to that later, but moisture content is a variable that has a big influence on the soil thermal conductivity. In oil applications, we already discussed, wet soil is the worst case situation, but the analysis of soil thermal conductivity is basically identical. The only thing is that the focus might be on the saturated situation rather than the dry. So there are some special reasons why people perform or encountered in soil thermal conductivity measurement. First of all, some surveys are done just to detect unexpected soil properties. So, for example, the survey might be along several kilometers of high voltage cable trajectory, but if there's some change in the properties, by doing regular measurements, you might be able to detect soils that are not behaving as normal. Also, you might encounter soils with, for example, not homogeneous, filled with rocks or volcanic soils or organic soils. That might also be of interest. And last but not least, in some cases, like in the Netherlands, soils are always saturated. So that's also a situation in which you might analyze, because then, for example, on the ocean floor or in the Netherlands, which is basically a swamp, you can engineer your whole high voltage cable or oil pipelines knowing that the soil is always saturated. So those are special cases. So what you should realize is, well, a basic rule set. You might have different soil particles. However, as a general rule, the particles are good conductors, and air insulates. So particles are basically broken up rock and crystal, so they might be conduct like glass or better than that, and air insulates at least a factor 10 better, so air is a clear insulator. The second factor is soil might contain water. Usually that's variable, but water conducts. However, not as good as the soil particles. You might also encounter organic material. Organic material is basically leaves or wood or whatever. Acts basically as an insulator, so somewhere in between air and water. However, organic materials sometimes get saturated, so then they go to the water value of 0.6. Sand particles conduct better than clay particles. And as a final thing, you can picture a dry soil as just particles with air in between. If the soil gets moist, this moisture will immediately creep between the soil particles and create bridges of water between the particles. So in that case, air is replaced by water, and the water has at least a factor 10 better thermal conductivity. So in other words, the change from air to water is really important. So here a graph of what to expect, and here on the vertical axis there's the soil thermal conductivity, and it basically varies between, let's say, 0.3 and 3. So 0.3 more or less like a plastic, 3 more or less, well, let's say 1 is glass, 10 is stainless steel, somewhere in between those. Water is 0.6. Here on the horizontal axis, the soil water content in, well, you could read it as percentage. So 5%, 10% by weight. So I'm gonna explain about 4 different soil types, which is graded sand, sand, clay silt, and clay. Let's start with the sand. So here, that's this graph here. What you see here is that dry sand is basically an insulator. So, and as soon as you get a little bit of humidity, there's a very steep increase. That's the water building bridges until you reach about 20% by weight, and it tops off at around the thermal conductivity of 2.5. This percentage by weight is about the maximum. That's the volume that was originally occupied by air, now replaced by water. So here you get to the saturated condition. Graded sand means that you have large particles of sand, but in between there are small particles of sand. So what you see there is that there's the maximum of water content is lower because there's originally less space occupied by air, and also that means that the water content can never reach the same level as with the sand, which is the same particle size, but the fraction of soil particles is higher. So in the end, you reach a higher thermal conductivity already at a lower water content. Then there's clay here, where you can see that basically the water content can, as a mass fraction, can be higher, but the clay plates, it's not a grain, but more like a plate. The overall thermal conductivity will top off at a lower value than for sand. And then finally, a mix between sand and clay silt, lower maximum water content, top thermal conductivity, about the same as clay. So you can already get some feeling what happens. What is important to realize is that soil moisture is a major factor in determining the thermal conductivity, and even a small change in soil moisture content will mean a very large change of thermal conductivity. So what do you do when you do a measurement? Well, so you put the needle in the soil. Don't be surprised if repeatability is bad. As was explained in the earlier section of this presentation, there's many possibilities for experimental orders, but also the dependence on soil moisture content is very strong. So if you perform a measurement, it's wrong to assume that the soil moisture content in your entire sample is the same. Also, from one depth to another depth, there might be a dramatic change in moisture content. Also, the interpretation of the signal is difficult. You have to look for a linear part of your graph. That's a manual job, and if you have some experience, you know that the choice of this graph has a big influence on your end result. And last but not least, if you have a soil that is not entirely dry and also not entirely saturated, then heating too much might mean local evaporation of water. That's an experimental error, of course, but please watch out for that. You can experiment by, for example, working at different heating power levels and look if the result remains the same. Overall, it is not easy to claim high accuracy in soils. If you attain an accuracy somewhere between 3 and 10%, you should be happy. In some cases, you can do better. For example, if your soil is completely dry or completely saturated, there you have a nice environment for the measurement. You cannot evaporate water, that's one thing, and the homogeneity of your sample is better. It's simply completely dry or completely saturated, so that's easy. As an overall impression of the uncertainty, Huxley often uses this formula, so try and experiment with that. Yeah, this is the end of our lecture. I would like to thank you for listening to us. You can find more directions in the manuals of the products, and we're always there to help you. So please write us an email in case you have further questions. Thank you very much.